Hey, what's poppin' party people? We are going to talk about the next thing in our unit. We're going to talk about velocity, speed, and we're going to learn our first real physics formula today. We're going to learn it with all the sweet physics variables. We're going to learn all the units of that thing, and then we're going to solve a couple of problems with it. So today what we're going to talk about, oh man, I just messed up my pen. I set it up and I forgot, but c'est la vie. All right. We're going to talk about velocity and speed and the difference. I didn't write the word difference, but distinguish between them. We're going to formalize, which means we're going to really nail it down, talk about definitions and stuff. The relationship between velocity and displacement. We'll revisit that idea later. We're going to have a whole lesson just on graphs. Today, we're really going to focus on definitions and formulas, and then we'll come back and revisit some graphs in a day or two. And we're going to use the formulas to predict the future, which is really what we want to do, right? Your next words are going to be, wow, no way. I got you so hard. Crazy. I know. So basically, we're going to turn you guys into wizards. It's going to be tight. You're going to be omniscient pretty soon. So let's get into it. All right. Let's talk about the vocabulary first. Velocity is how fast something's moving. Okay, Mr. Barton, no surprises there. The important part here is that velocity is a vector, which means you have to tell me the direction of that vector. Okay? Let's talk about vectors really quick. Let's talk about specifically the unit we're in, which is 1D kinematics. One dimension means a single line, and you can move forwards on that line, or you can move backwards on that line. There's no y-axis. You can't go left or right. It's forwards and backwards, and that's it. 1 degree of freedom. So rather than discuss everything in terms of forward, backwards, north, east, south, west, 32 degrees and 15 minutes and 2 seconds, counterclockwise from north, we're not going to mess with that. The way we are going to distinguish direction is with positive and negative. Typically, we will just assign a direction a sign. Usually, you follow math conventions, and forward or to the right is positive, and left or backwards is negative. It's completely arbitrary. What's really nice about being a physicist is it's actually like being a wizard, and it's whatever you say it is. The important thing here is consistency. So if I say he has a velocity of 5 meters per second, you're going to say that's not a vector. What's the direction? Well, it's positive. So the direction's whatever direction I said is positive. It's forward or up, or you know what I mean? So I understand in the last lesson that I made a big deal about you having to tell me a direction. We are now going to say positive and negative can indicate direction. That makes it difficult. When we talk about speed, which is how fast something's moving, speed is a scalar. If I say speed, I don't actually remember the real variable for speed because no one ever talks about it. We'll say S, even though that's path length, that's distance. Speed equals 5 meters per second. There's no way to tell by looking at these which one's a vector and which one's a scalar. So it becomes based on context. So I hate that physicists do that, but they do. So forgive me if I don't formally tell you. I'll make a big deal about it at the beginning. When we're solving some problems, I'll say, okay, I'm going to say forward is positive, and that's the direction. So if you see a positive, it's a vector, positive meaning forward. But as the semester goes on, it's going to get a little loosey-goosey. Sorry, that's the way it is. I'm not perfect, so there you go. Leave a little bit of room here, because after we talk about the next slide, we're going to come back and add a little bit of definition to velocity. Okay, so for right now, you want to know intuitively, it's how fast something's going. It's the vector version. Speed is how fast something's going. It's the scalar version. Speed is actually also the absolute value of velocity. So if I say my velocity vector is -5 meters per second, this negative is telling me the direction. So if I remove the directional information, now it's positive, right? I just took an absolute value. So that's one of the formulas we'll talk about today. But okay, leave a little bit of room under velocity, because we're going to add a sentence here, and then we'll be rocking and rolling and ready to physics. Okay? All right. Let's talk about these equations. Okay? We're going to label these. We're going to take a peek at some units, and then I've got one more thing to talk about. Two more things to talk about, then problems. Okay? So this is your displacement equation. We are going to amend this in 1 to 2 days. We're going to add another chunk onto this, but we have to learn another physical concept before we can add it. Otherwise, it's just letters. So this is our displacement equation. It tells us the final displacement. That's what this subscript F is. So final displacement equals initial displacement plus velocity initial times time. Don't worry about this velocity initial. We're not going to change velocities today. Today is going to be constant velocity. So if you want to think about it as where you start plus velocity times time, or how fast you're going times how long you go, then you'll be fine for today. But later it becomes important. So just realize that it's there kind of as a heads up. But it's where you end equals where you start plus your velocity times time. Okay, let's take a peek at some units here. Displacement is measured in meters. Okay. Initial displacement, that's where you start at the beginning. Okay, where you start, or location, a distance from something. I start 3 meters past the fire hydrant. That's also a distance. Let's look at the units of velocity times time. The units for velocity that we're going to use 90% of the time after we actually learn how stuff works is meters per second. And then time is seconds. So if you take a meter per second times seconds, the seconds cancel, and it's a meters. So notice how the units of this entire equation agree with one another. Meters equals meters plus meters. And this allows us to add these two things. Before I said you can't add two things if they have different units. But when you multiply these two things together, the units simplify so that it has the same units as the other term, and you are allowed to add them. Okay. So final position equals where you start plus how fast you're going times the amount of time you go for. Simple enough. This equation is V bar, and this bar over there means average. Whoops. Sorry, English got in the way again. Average velocity. And let's maybe talk about the formula, and then we'll formally define average velocity. Okay. Your average velocity equals delta. That's the Greek letter delta. It's technically the capital Greek letter delta. There is a lowercase version, but delta x, or delta position displacement, divided by delta time, or t. So average velocity equals delta x over delta t. Units for change in position are meters. Units for time are seconds. There's a fraction, meters per second. There we go. So we get our units back to what we expect our units of velocity to be. And just in case we're a little confused about these deltas, what a delta means change in. So delta x means change in position or change in displacement. You're going to notice that I use the word position for displacement a lot. They're more or less interchangeable. If you actually want synonyms, displacement is pretty much equal to position. That's not 100% true, but they're pretty interchangeable. Okay, so delta x means change in position divided by change in time. The formal way to write this out longhand is the final position minus the initial. Final minus initial anything is change in that thing. For example, if I end 6 feet from the wall and I started 3 feet from the wall, I've moved 3 feet, right? So final minus initial is change in. Oh, that should be an F, not a T. Okay. So change in position divided by change in time. Final position minus initial position over final time minus initial time. Okay. This is the average velocity. When we say average velocity, we do not mean velocity plus velocity plus velocity divided by the number of velocities. It's not the mathematical average. It's not the mean. Does not equal the mean velocity. When we say average velocity, what we mean is if you are driving not the same speed the whole time, because very rarely you do. Think about it. If you leave your house, right? What do houses look like? Something like that, right? When you're driving out of your house through your neighborhood, this whole section is probably 25 miles per hour. Then you turn onto like a big road, and then this is 45 miles per hour. But in Arizona, you drive 55 miles per hour, right? And then you'll get on like a freeway, right? A big highway interstate type thing. And this is 55 miles an hour. But in Arizona, we go like 70 miles per hour instead because that's safer. So you're not going to move the same speed the entire time. This tells us if you are going to go one speed for the entire trip, what would that speed be? So if I left my house and I wanted to just put it in cruise control and then never change it and arrive at exactly the same time as if I do all this speed changing, what is that cruise control speed? The average speed. And we'll leave it at that. Okay. We'll see an example and it'll make a little bit more sense, but just know that this is not the mean. Do not add your velocities together and divide by the number of velocities. Use this formula, which is total distance driven or total distance covered divided by total amount of time taken. Okay. And then the last one we need to talk about is speed equals the absolute value of velocity. Basically, if you're going 5 meters per second backwards, so negative 5 meters per second, your speed is 5 meters per second. We don't care about the direction. We just care about the number. So if you take the absolute value of velocity, you'll get the speed. Good? All right. So let's talk about the physical meaning of velocity and some units, right? We're also going to spend a little bit of time discussing the word per, because you've heard me say it a few times now when we talk about fractions, but you've probably never sat down and tried to define the word per, right? It's a weird word. It's one of those words like the. Like, what does the mean? I have no idea. So we'll talk about that as well. So let's look at this question. It says, you're walking 2 meters per second. How far will you go after 3 seconds? Let's not worry about the formulas. Let's think about it. You go 2 meters per second. How far will you go after 3 seconds? You probably have a gut feeling right now that it's 2 meters per second times the number of seconds you go, right? Times 3. And you're right. So we're going to go 6 meters. All right. We can also see this in our formula. X final equals X initial plus velocity times time. I don't tell you a starting position, so we'll just assume it's 0. So it's my velocity, 2, times my time, 3. I'll go 6. That's not a 6. Try again, Mr. Barton. 6. Anyway, okay. But let's break this down. This is 2 meters per second. The word per means for every, hold on, hang on. I'm trying to talk and think at the same time. For every one. So this is 2 meters for every 1 second. Okay. So if we drew maybe a one-dimensional graph, we'll just draw our displacement. Here's 0. We're going that way. So 1 second happens, I go 2 meters. Another second passes, I travel an additional 2 meters, and now I'm at 4. I travel for another second, I go another 2 meters, I'm at 6. So for every 1 second that passes, I travel 2 meters. This is how quickly my position is changing. And you're going to say, Mr. Barton, this seems incredibly obvious. Like, listen, those kids that hide behind the bleachers and smoke that funny smelling thing, and it smells like a dead skunk at the football games, I bet those kids get this. And you're wrong, but I appreciate your faith in your classmates. So what velocity is it is the rate of change of your position. Let's go back and amend this definition. Velocity is the rate, of change of, I keep saying position. The formal definition for this class is displacement. Okay. Write this down, memorize this, get a tattoo of this. When you guys who are in calculus learn this wonderful, magical thing called a derivative, let me know, and then we'll have another conversation about this. Let's revisit our equation one more time. Velocity is the rate of change of displacement. Let's math the heck out of this thing. We're going to like corner this thing in a dark alley, pull out our arithmetic, and beat this thing to death with mathematics. Okay? All right. This looks like an equation you know from your math class. Okay, the thing by itself on the other side of the equal sign, that's always y. Equals. What's the only equation? Let's see, y equals. Slope-intercept form. mx plus b. Mr. Barton, this is one thing, not two things, even though it has a sub. Okay, fine, kids. Let's use the associative property of addition, which says we can change the order of the commutative property of addition, which says we can change the order of addition and nothing changes. Y equals b plus mx. This is where we end. This is where you start. Velocity is your rate of change. T is your input variable. It's your independent variable. So we can see velocity is quite literally the slope or the rate of change of position or displacement. Okay? I know, math is wild, kids. Like, I love it. It really makes you feel like, you know what I mean? It really makes you feel like a wizard. It makes you feel like one so much. It's so tight. You're going to love this class. So this is y equals mx plus b. Velocity is literally the slope or the rate of change of displacement. And now we're going to go learn something else. Okay. I think I've hammered you enough with definitions and nuance and finer details of mathematics and definitions and all that beautiful stuff. Okay. Don't panic. We're going to solve some problems. Let's make this stuff concrete, right? It's great for a wizard to read the books, but eventually he's got to take his wand and Wingardium Leviosa. You feel me? So let's go wave our wands and let's practice casting spells instead of simply reading theory. Okay. Here are some tips on how to properly wave your wands without hurting yourselves. Step 1, stay calm. Okay. You are about to enter the wonderful world of physics where everything is a word problem. And if I know anything from Algebra 2 and pre-calculus, students hate word problems. They detest word problems. And it's because they don't do them often enough for them to become fun, right? It's like learning to ride a bike. The first 5 minutes you ride a bike, you fall down, you scrape all the skin off both knees and your elbow, and your dad goes, son, it's not that hard. Just pedal. Just hold the handlebar straight. And no, son, listen, right? But eventually, you start riding bikes, you're doing wheelies, you're doing bar spins, boy. Oh my gosh, riding bikes is so tight. So you need to get good enough at word problems to where they're fun and we're not panicking anymore. Okay, we're going to take the training wheels off slowly. So step 1 is stay calm. You're learning a new skill. You're becoming comfortable with it. We're going to break things down very slowly so that they are digestible and engageable for students. Okay, they take some dissecting. My first real tip for you besides quit freaking out is read the question, which is usually the last sentence first. If you go that far, how far did you travel? Okay. If you read the last part first, what was your average velocity? Okay, I guess I can't circle. What is your average velocity? These things are going to give you some sort of direction. They give you a goal. I wish I could spell. They give you a goal to work towards in your problem so that you're not just wandering blindly through formulas and nuance. Next, once you have this goal in mind, you want to identify some equations that you think are relevant. Okay. You're not going to nail that every single time. You're going to be like, it says find this thing. The formula for that thing is this and this. And you're going to pick this one when you need that one. Okay. This also takes practice. But once you have a goal in mind, it's a good thing to go look for some equations that involve that goal. If you're looking for average velocity, you should probably look at an average velocity equation, right? Write down the variables as you come across them in the problem. So you go, you're traveling at 5 meters per second in the forward direction. Velocity equals 5 meters per second. Write those things down. Literally just make a list of all the variables you know, and maybe even make a list of ones that you wish you knew based on this formula you got from your goal. And go, okay, so I've got velocity, I've got time, I need delta x. What is it? And this will help you set up problems. Okay. The last thing, this is more like philosophic advice. It's not necessarily problem-solving advice, but don't be afraid to change things in general, right? Say you read something, you go, velocity final equals 5 meters per second. And then you realize that that was actually velocity initial. So go back and change it. It's okay. You can make mistakes. I just grade your answers. I don't grade your work. Just go ahead and scribble that on initial. There we go. Disclaimer, I just realized. V initial, I, and subscript 0, not. These are the same things. I accidentally switched between them. Additionally, I write my V's like this, because when I do them like this, sometimes they look too much like my U's because I'm sloppy and rush too much. So if you see this, it's a V. If you see this, it's probably a U. Okay. So don't be afraid to go back and make changes. If you realize you made an error, fix the error. Don't try and force the error to work. It probably won't, and you'll probably give yourself an aneurysm. Lastly, try something else. Like I said, you think it's this equation here, but it's really this one here. Go, okay, that's the only equation. It's this equation. That's the one x final equals. Okay, but there are other equations where velocity is. So if you're trying to find this velocity, maybe go see if there's another equation later. That's not going to apply too much today, but it's good advice in general. All right, let's go do some problems. All right, let's talk about using the displacement equation. So it says you are running at a brisk pace of 5.4 meters per second. If you go on a 25-minute run, how far did you travel? Okay, I already broke my own advice. I should have started at the end. How far did you travel? Okay, this sounds like a displacement to me. So I'm going to say final displacement, that's a question mark. That's what I'm looking for. Okay. What equations do I know that involve final displacement? The displacement equation. Let's write that down and investigate it, shall we? X final equals x initial plus v naught t. Okay. So I've got to find this one. I need to know x initial, v initial, and t. Let's go back and read the question again, specifically paying attention for these things. You are running at a brisk pace of 5.4 meters per second. Okay, that sounds like a velocity to me, and I can tell because of these units. Meters per second, a distance divided by a time, that's definitely a velocity. So velocity naught equals 5.4 meters per second. You go for a 25-minute run. That sounds like an amount of time to me. T equals 25 minutes. Okay. And that's it. We're out of numbers. There's nothing else in this problem. Now it just asks me how far did I travel. What is x naught? What is my starting position? If they don't tell you a starting position, what you want to do is you want to assume. You don't want to assume anything because you know what they say about assuming. You have to be very rigorous and skilled at it to get it right. So what we're going to do is, because they don't tell us where they want the starting position to be, we're going to assign the value of 0 to it. We're going to say wherever the problem starts, wherever I start recording this 25 minutes of time, that location is where I say 0 is. That's the origin. So here's the origin. I run. We want to know, what is this distance? X final. Let's see. Let's go back and follow my advice from last video. What is X final? X initial. They don't tell us, so I say this is 0. I want to know what this is. It's a variable. It's X final. I know that it took me 25 minutes to make this line. I want to know, what is the velocity? How quickly did I transverse this line? Okay. We are almost ready to apply our formula. This is gone. X final equals velocity times time. The only problem we have now is that this is in meters per second, and this time is in minutes. If you do meters per second times minutes, do you see how these two units do not cancel anymore and give us a meters for our position? That's bad. You have to have units that agree. So we need to turn this into seconds the same way that we did in that prerequisite unit where we did unit conversions. So let's convert this to seconds really quick. 25 minutes. I know the conversion is 2 seconds. So the minutes has to go on the bottom. The seconds has to go on the top so that the minutes cancel. There are 60 seconds in 1 minute. Aha, that'll do it. Cancel. 25 times 60. You grab your handy dandy calculator. 60 times 25, I'm sure it's really obvious, is 1,500. 1,500 seconds. Now that we have this in agreement, now that our units are the same, now we can plug them into this formula. So X final, that's what we're looking for. We leave it as variable, equals velocity, 5.4. You can put the units in. I tend not to because I do this work of making sure they agree before I start plugging numbers in. If you tend to forget this, you might want to put the units in here to remind yourself, but I tend to omit them because I think it makes it look sloppy and I get confused. So velocity times time. Make sure we use the seconds. 1,500. So now we multiply 5.4 times 1,500, and we get that we have gone 8,100. The seconds cancel the seconds. Meters. So we have gone 8,100 meters, or 8.1 kilometers. And if you really felt like it, you could convert that to miles, but I'm not going to make you. When you are doing these problems on your homework, I will tell you what units to give me the answer in. I'm going to try and probably pick the easiest ones. I'm not going to make you solve it in meters and then convert it to miles. That's masochism. Sadism? Sadism. I won't do that to you. All right. Cool. All right. Let's look at the 2 average velocity problems, and I think I need to add one more displacement example, and we'll make it up on the fly. Those are really fun, but I want to show you one more type of strategy. Okay. It says you go for a bike ride and check the clock when you leave and when you get back. And you were gone for an hour. An is a fancy word for 1 hour and 15 minutes. Your GPS tells you that your ride was 16.25 kilometers. What was your average velocity? I forgot to do it again. We should have read the question first. Average velocity, you say? What's the formula? Average velocity equals change in position over change in time. If we really want to know, X final minus X initial over T final minus T initial. All right. So what's our average velocity? Let's go back, read one more time. This time we'll write down our or variables as we come across them. You go for a bike ride and check the clock when you leave and when you get back, and you're gone for an hour and 15 minutes. So they don't tell us when we started. They don't say I left my house at 2 o'clock and I got back at 3:15. What they're telling us is the elapsed time. They're skipping this piece here and they're just going straight to delta t. They're saying the total amount of time taken was 1 hour and 15 minutes. So we'll write it down as delta t equals. Delta t equals 1 hour, 15 minutes. And as you guessed it, we're probably going to have to do some unit conversion stuff here because it's not good to have two different units in one value. That's awful. Your GPS tells you that your ride was 16.25 kilometers. We're going to also kind of ignore the fact that my ride was probably something like this, where my displacement, because I start and end at my house, my displacement, I don't know why I drew that, is 0. Okay. So, we're doing distance. We'll fudge it a little bit. It's not that big of a deal. We will be much more strict about these definitions once we have more to work with. But because we have so little to work with right now, it's kind of hard to make up real situations that use literal displacement. So we'll fudge it. The distance I traveled, is 16.25 kilometers. Okay. So we can just throw these things right into this equation after we make these 1 unit. Let me show you a very quick maths thing that students always mess up. 1 hour and 15 minutes is 1.25 hours. And you're going to say, no, it's not. It's 15 minutes, not 25 minutes. Okay, but an hour, it's 15 minutes out of 60 minutes for the full hour. 15 divided by 60 is 1/4. It is a quarter of an hour, but kids forget that hour is base 60, not base 100, so it is. So this is 1.25 hours. All right, let's just plug these numbers in. Change in average velocity is 16.25 kilometers divided by 1.25 hours. We divide this and we get 13. And now let's talk about units because it's not meters per second. Did I plug in meters? No. I plugged in kilometers per hour, not seconds. If I wanted meters per second, we'd then have to do our unit conversion stuff that we practiced last unit. But if I give you something in kilometers and hours, I'll probably be really nice on the homework and ask you for the answer in, come on you guys, kilometers per hour. Okay, this is the easy version of average velocity. Let's go talk about the hard version where students goof it up all the time. Okay. You run do-over. Let me try and read that again. You run at 5 meters per second for 10 minutes, then pick up the pace to 6 meters per second for 20 minutes. What is your average velocity? Okay, this is a very tricky problem. So let's look at this. Average velocity. We need total distance traveled divided by total time elapsed. Okay. Let's find our, let's read this again. 5 meters per second for 10 minutes. Okay, I'm with you on this one. Time equals 10 minutes. This is a velocity though. This is not a displacement. All right, let's write it down anyway. Velocity equals 5 meters per second. Okay. Then you pick up the pace to 6 meters per second for 20 more minutes. Okay. I've already got a time and I've already got a velocity. So let's call this first set time 1 and velocity 1. And let's call these velocity 2 and time 2. Okay. So we have our total amount of time. It's 10 minutes and then 20 more. That's 30 minutes altogether. So we have our total time. We don't have a total distance, though. That's the problem here. So we need to think, how can we figure out how far we went? Well, luckily for you, you just learned an equation that tells you how far you go, right? Okay, how far did I go? We want to know this here. Actually, we kind of want to know delta x, right? Delta x equals x final minus x initial. Let's subtract this to the other side. X final minus x initial equals v naught t. Delta x equals velocity times time. Okay, so they want us to multiply these together to get that delta x. And you're thinking, Mr. Barton, I would never figure that out on my own. Maybe you would. Maybe you're brilliant and you would figure it out on your own. I'm not going to discredit you and say you can't. But a lot of students seeing this, they go, how do you expect me to figure that out on my own? And the answer is, I don't. That's why it's an example problem, and I'm showing you how to do it. So, okay. So what we're going to do is we're going to multiply these together to get our distance traveled. Then we're going to plug that into this equation, and then we'll figure that out. So let's set this off to the side a little bit. What's the important part? I don't need all this. The important part's just down here. Delta x equals velocity times time. That's the important bit. Okay, so we're going to multiply our velocity times our time. Secondly, right? Yeah, sweet. So delta x equals, delta x1 for this set is 5 meters per second times, oh wait, we can't multiply these, right? The seconds aren't going to cancel with minutes. We have to change this into seconds so that they agree. I don't want to turn this into minutes. It'll be a fraction. I'm scared of fractions. So 1 minute is 60. So we're going to multiply this by 60. This is 600 seconds, right? Okay. So 600 seconds. This is delta x 1 equals 3,000 meters. All right, seconds cancel. There we go. Convert this. If 10 minutes is 600 seconds, double that is double that. So this is 1,200 seconds. So delta x2 equals 6 times 1,200. So this is going to be 7,200 meters. Dang, we ran over 10 kilometers. All right. So average velocity is total distance traveled. Let's add these together. 3,000 plus 7,200 is 10,200 divided by total time. So we want it in meters per second probably. So let's put the seconds. 600 plus 1,200 is 1,800 seconds. Then we put this into our calculator very carefully. 10,200 divided by 1,800 equals 5.6666, repeating, so we'll round to 67 meters per second. Okay, what an ordeal. I know, exhale, walk it out, walk it out. All right, you're fine. We got this. Cool. All right, that was fun. I like that. So there we go. There is the slightly more challenging average velocity problem. You'll have maybe one of these on your homework, maybe a couple of these. So you'll be all right. Good thing I have this extra slide here. Let's do maybe one more displacement equation. And this will be way easier than what we just did. Okay, let's say you're going to race to a tree, right? Here's our tree. Pardon the terrible drawing. And you're racing your friend or whatever. He's going to start at the fire hydrant. What do fire hydrants look like? Something like that? I don't know, right? Something like that. That's pretty close. So he's going to start by the fire hydrant. And your friend is pretty lean. So he says he's going to give you a 3-meter head start. So here's you. What do you look like? There's you. You are not all connected. Okay. You get a 3-meter head start. We'll say this thing is 25 meters away. And you run at a known velocity. Let's say you run at a velocity, your top speed, right, is 10 meters per second. That's actually pretty fast. I'd be surprised if you guys could run 10 meters per second. No offense. Okay. We want to know how long does it take you to get to the tree. Okay. So let's break this down. I understand it's not a word problem, it's a picture problem, but you get the idea. So the only equation we know is displacement equation. Our displacement equation is x final equals x initial plus velocity initial times time. We want to know time. All right, let's pick out the rest of these variables. Our starting position, they gave us a head start, 3 meters initial. Where are we going to end up at? The tree, which is 25 meters away. That's our final displacement. And our velocity is 10 meters per second. Don't worry how you got going that fast yet. All right, let's plug these in and solve for t. So we have 25 equals 3 plus 10 times t. We don't know what t is. Meters, meters, meters per second. All things are in meters. Because we're putting in seconds, our time will come out in seconds. Now we just do some algebra. Subtract 3. 22 equals 10 times t. We divide by 10. And we get 2.2 equals t. Then you have to ask yourself, what do I measure time in? Well, we put in a number with seconds, so it's going to come out in seconds. Okay, so for your displacement equation, there's a bunch of different tricks you can do. Use it wisely. I leave the fate of the universe in your hand. Be careful. Don't divide by 0. Make sure you use this responsibly. With great fortune telling comes, I don't know. Cool. Hop in the WebEx if you need help. See you guys next time.